So the standard way typically of drawing the XYZ coordinate system is typically drawing like this. So you have Y and Z going that way, and then X coming out at you. And we usually label the X, Y, and Z on the positive axis, right? So this side is the positive X-axis, this is the positive Y-axis, this is the positive Z-axis. And you certainly could label it a different way, right? If you wanted to, you could do it as, I don't know, Z, X, Y. Now, let me tell you something that would be wrong. So you should stick to this, is what I really should say. Right? This is the way most every teacher is going to do it. This is what you're going to see all the time. But if for some reason you decided it was convenient to rearrange them because maybe the way the equation looks, it looks nicer to do a different way. I just want to tell you, there are wrong ways to do this. That would be wrong. How do I know that's wrong? Here's the idea. So there's something in math, in three-dimensional math and physics, called the right-hand rule. Take your right hand, you point your fingers in the direction of the x-axis. You curl your fingers, take that to your right hand. You curl your fingers in the direction of the y-axis, and then your thumb has to stick in the direction of the positive z-axis. So fingers positive x-axis, curl towards the positive y-axis, thumb has to stick in the positive z-axis direction. If we do that here, if you take your fingers and put them in the x direction, and then curl them up towards the y direction, your thumb's sticking in the wrong direction for the z-axis. So yes, you can reorient things if you want to, but you do have to obey the right-hand rule. Really, you shouldn't be reorienting things. You should just use this. But if for some reason you wanted to, right-hand rule is where it's at. Okay. But then we can plot things, right? We can say, like, I want to keep not grabbing the wrong pen. I want to plot the point, I don't know, 2, 4, 6. Plotting a point in 3 dimensions is kind of a pain. So here's what I'm always thinking about when I'm trying to plot things in 2 dimensions. The y-axis and the z-axis, the spacing looks the same for them, right? They're both, I kind of think of the YZ plane as the plane of the board, right? The board is the YZ plane, and then the x-axis is pointing at you. Except, right, we can't draw that perfectly because, you know, I'm drawing a 3-dimensional space on a 2-dimensional surface. So what I'm trying to get at is that the spacing in the x and the y, in the y and the z direction should be the same. So going over 6, going up 6 should look like the same amount. But coming out at you 6 is not going to look like the same amount of distance because I've taken this distance, but then I've tilted it, right? If I take something that's this long and I point it at you, oh, it doesn't look as long anymore. So these marks here don't get to look as long. Maybe they're like this. So that's kind of an important detail. So then if I want to go 2 in the x direction, 4 in the y direction, and 6 in the z direction, I'm going to go 2 in the x direction, and then I'm going to go 4 over. I'm going to go over 4. Whenever I'm going in a direction, x, y, or z, I'm always going in a direction that is parallel to that variable's axis. I know this doesn't look perfectly parallel because my drawings are not great, but right, I went 2 in the x direction, so I went over to the point 2, 0, 0. And then from that point, I went 4 in the y direction, parallel to the y-axis. That's probably too much, right? Because 4 is like right there. What I'm really actually going to do to find that point is I'm also going to go 4 first in the y direction to the point 0, 4, 0. And then I'm going to go parallel to the x-axis, a length of 2. So I'm really kind of finding where this point, that line, and this point, that parallel line meet up. And now I have to go 6 in the z direction. So I have to go 6 up. So I'm going to start here at 0, 0, 6. And I'm going to go both 4 in the y direction. This gets me right there to the point 0, 4, 6. I'm also going to go from here, I'm going to go 2 in the x direction. So that point right there is 2, 0, 6. And then finally, I'm going to go 4 over, I'm going to go 2 over, I'm going to go 6 up to find that point there. So there's the point that I was looking for. Sorry, trying to always find my good pens. Right there, there's your point 2, 4, 6. Typically, oh, sorry, Chang. Let's see you come in there. Do I have my volume off? I don't think so. Right. Typically, when you're trying to just plot a point in three-dimensional space and it's not on one of the axes, right? If all of your x, y, and z coordinates are all non-zero, typically the way I kind of think of it is you're drawing a box where one corner is at the origin and the corner opposite of it is the point you're trying to plot. Fun times. Again, you shouldn't have to do too much three-dimensional plotting or graphing of things, I hope. She did talk about in class how there are 4 quadrants, right? If you're in the, oh wow, that's not the straightest line I've ever drawn. Let's try that again. Okay. So, right, there are 4 quadrants. X, Y, this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. And if you're in the, so the thing I always think about with the quadrants is the first quadrant is always the one where everything's positive. So first quadrant, X is positive, Y is positive. In 3 dimensions, you're cutting three-dimensional space in half 3 times. So if you cut something in half, you get 2 pieces. If you cut it in half again, you get 4 pieces. If you cut it in half again, you get 8 pieces. So we've got 8 octants. And I don't know how to label them, except I do know that this part here, right, the upper front right part, right, all this jazz over here, that's the first octant. The one where every variable is positive. This point, 2, 4, 6, is in the first octant because X, Y, and Z are all positive. I don't think there is a standard way of labeling the rest of the octants. Like if someone said, where's the 5th octant? I'd be like, I don't know. I don't think there is one. There is definitely a 5th octant. There's just not a standard 5th octant. Whereas there's definitely a standard way of labeling the quadrants of the X-Y plane. So I don't think anyone should ever be talking about the 3rd or the 4th or the 12th, well, not the 12th, there's no 12 octants. But you get the idea, I hope. So the reason I mention this is because a lot of times people will say, like, let's look at this shape that's bounded in the first octant. Kind of like when we find areas of regions that are in the first quadrant. That's why someone might use, that's really kind of the only reason why someone is usually talking about octants is they're like, oh yeah, I want to find this region, but only in the first octant. Let's see what else we got here. Yeah, cool. Actually, that kind of goes along with, let's talk about the planes for a second. So I'm only drawing the positive parts for this, X, Y, and Z. We do know that they continue on in the other directions, right? There's negative Y, there's the negative X direction, there's the negative Z direction. What I'm interested in mentioning here is the various, let's see if I got more colors, got some good colors. Yeah, okay. I'm sure blue will work. So this plane down here, which I know, right, it's not finite, a plane is infinite. And it keeps going in each of these directions. So that plane right there, this is the XY plane. And its equation is z equal to 0. And I know she mentioned this in class that, so when you have an equation of a thing, if you're missing any of the variables, the thing you're drawing gets to kind of be free in that dimension, right? So here in the XY plane, which is, I mean, also, right, which certainly does extend this way and that way as well, right? But again, I can't draw for infinity. So in the XY plane with z equal to 0, basically saying, okay, well, I can't go up or down, but that's my only limitation, right? X can literally be anything. Y can literally be anything. So when I graph z equals 0, I'm saying, okay, X can be anything, Y can be anything, Z is 0. There you go. In a similar way, let's try and draw this. The xz plane is given by the equation y equal to 0. Because again, you can't move left or right, but you can totally move forwards, backwards, up, down, as much as you want, because there are no x's, there are no z's in our equation. And lastly, I'm sure you guys have already guessed what this last one's going to be, right? Here we have my favorite plane to graph in 3 dimensions, the YZ plane. Why is it my favorite plane? Because it's the one that looks like it's the board, right? The YZ plane is the board. And that's the equation x equal to 0. Cool. So that's kind of a really important idea, is that if you're missing a variable, regardless of actually how many dimensions you're graphing, and whether it's in 2 dimensions or 3 dimensions, if you're missing a variable, that means you can extend your graph in the direction of that variable. In the direction of that variable as much as you want. Let me show you a couple examples. So what if I wanted to graph the line? Let's try to make our lives easy, James. Sure, fine. So here's an equation of a line. 2x plus 3y equal to 6. It's not written in the usual y equals mx plus b form, but it's definitely a line in 2 dimensions because you have x to the first and y to the first. We could solve for y, right? We could write y equals negative 2/3 x plus 2, but I don't want to. You don't want to either, because the nice thing about writing the line this way is it's super duper easy to see what the intercepts are right off the bat. So if I was going to graph this line, I can see that if I set x equal to 0, y has to be 2. If I set y equal to 0, x has to be 3. So to graph this line, I'm going to go through the points, x equal to 3, y equal to 2. And there's my line. Great. But now I want to ask, what's this going to look like if I tried to graph the same equation in 3 dimensions? So I was going to graph, still actually, I'm literally writing just the same thing, 2x plus 3y equal to 6. But now we're taking this and we are doing it in the XYZ 3-dimensional coordinate system. So I find it useful to be able to imagine that, okay, I'm taking this and I'm kind of reorienting it, right? So it's too bad that it's not kind of oriented the same way as the XYZ coordinate system, but it's not. Yeah. No, that's not super cool. So, okay, fine. Sorry. So the idea here is that I'm thinking, okay, I'm laying this flat, but I'm also turning it so the x-axis is pointing at you. So I'm kind of thinking, okay, here's my X, here's my Y. I know that my, let's see here. I know that my x-intercept is 3 and my y-intercept is 2. So here's my x-intercept that's 3. Here's my y-intercept that's 2. And here's the line. Sure, the line that goes through them. But then there's no z. So we can extend. Let me draw this a little further here. We can extend in the z direction. Not only can we have to extend in the z direction as much as we want. Now, typically, when I'm drawing this plane, I'm trying to draw it so it looks like it's kind of parallel to the line that is going through it. This is probably not the best drawing ever. It's definitely not the best drawing ever. But if you wanted to make it kind of look a little better, you could kind of say, well, look, the plane is kind of in front of all these axes here. So if you really wanted to, you could say it's going to be like, I'm going to try and make it look more three-dimensional, meaning, and I just kind of erase like all my stuff here. Oh, sorry, someone's trying to come in. I just let them in. Okay. So oh, grab this part too. Sorry. So maybe that kind of looks like, oh yeah, we can see this axis sticking out that way, and this axis sticking out that way, but the rest of these axes are behind the plane that I've drawn. Not super important, but just trying to kind of give you guys a visual of what things look like. The important thing here is that once you've drawn the line 2x plus 3y equals 6, then we extend that line in the missing variable direction, both in the positive and in the negative missing variable direction. The z can be anything. The thing I really think about it as, it's exactly like graphing y equals 4. We know how to graph y equals 4, right, in 2D. To graph y equals 4, it's going to be a horizontal line through the point 0, 4. Why is it a horizontal line? Well, because y has to be 4, and x can be anything. So we're taking this y value of 4 and then just saying, okay, extend it in the x direction as much as you want because there isn't an x. It's really the same idea, just we're upping the dimensions. So if you want to draw y equal to 4 in 3 dimensions, sorry. I want to graph y equal to 4 in 3 dimensions. So I'm going to go over 1, 2, 3, 4. So y equals 4 is right there. There's the point 0, 4, 0. And then I have to go in the other missing variable directions as much as possible. So I'm going to go up. I'm going to go down. I'm going to go forward. So to go forward, I have to go parallel to the x-axis. I'm going to go backwards. And then I'm going to try and draw like a plane looking thing. Again, I personally think you should try to draw the borders of your plane so that they look parallel to the various axes. Okay. Sure, that turned out maybe okay. There's your plane. Y equals 4. It's parallel to the xz plane. Y equals 0. Right? Just like, yeah. Yeah. Interesting. One way you could try to make it look maybe slightly better if you wanted to. Let's do a different one. if I was going to try and draw the plane, like say, I don't know, z equal to 6, one way you could try to make it look a tiny bit maybe better. Say, okay, I'm going to go right up to 1, 2, 3, 4, 5, 6. And then I'm also going to do that from like a couple other points. So maybe like from here, I'm going to go up to 6. And then from this point here, I'm also going to go up 6. So up 6. Can I do it? Yeah, perfect. It's that long. And then maybe from where these points would meet, I'm going to go up 6 as well. Okay, so right. So right, like here is my here's my horizontal plane z equal to 6. And it should extend right in every x or y direction. But I'm kind of drawing it this way so that you're kind of thinking of like if there was a light shining directly from above, it's kind of casting its shadow down onto the xy plane. So that's interesting. So certainly planes are not the only thing. Oh, I should actually let me talk about one more plane before we move on. So far, all the planes I've drawn have been missing a variable, right? You've had missing x or missing y or missing z. You can have all 3 variables. You could have something like 3x. Do I want to make it hard to draw? No, I don't. Plus 2y plus z equal to 6. Basically, your equation is the equation of a plane if the variables you have are all raised to the first power, right? So just like in 2 dimensions, you get a line if you have y to the first and x to the first, or just one of them to the first, right? But you don't have any like other powers. Same thing is true in 3 dimensions for planes. You have whatever variables you have. You don't have to have all of them. You have to have at least one of them. But whatever variables you have, if they're all raised to the first power, you're gonna have a plane. So here, this one's kind of like the easiest one to draw, kind of. So let's see, I'm gonna find my intercepts. So let's say 1, 2, 3, 4, 5, 6. Sure. So then we're just going to find our intercept. So let's see. If y and z are 0, by the way, to find an x-intercept, you're just going to set the other variables equal to 0. So to find the x-intercept, set y and z equal to 0. You're going to get x equal to 2. To find the y-intercept, set these equal to 0. You're going to get 2y equal to 6, which is y equal to 3. And to find the z-intercept, set these equal to 0. You're going to get z equal to 6. And then if you've got 3 points, that's enough to just purely define the plane. So I'm going to connect so there's part of my plane, right? It's this flat face thing that's kind of tilted back away from you guys, right? Kind of back like this. And it's hard to draw more of it. Like you could say, okay, well, it's going to keep going in that direction. It's going to keep going in that direction. It's going to keep going in all these directions. But usually we just draw the little triangle part and call it a day. So an example of a problem you won't see in this class, but is kind of just to kind of say something. Someone could ask you, not in this class, but the question that could be asked that's interesting is, what's the volume under this plane in the first octant? So then you'd be looking at, oh yeah, I want to see like what's all this? I want the volume of this tetrahedron. I'd be like, we got this little base here, and then all this stuff above it. That's not a question we're going to be answering in this class, but that's kind of the idea I was talking about when why you want to know what the first octant is, because people ask questions like that. Like, oh, okay. All right. So then, right, not all of our things have to be straight. We can have all sorts of different curves. So you can take any kind of shape, and if you're missing a variable, you're extending it in that direction. So what's interesting is that we kind of use the word cylinder. So if I say the word cylinder, I bet we're all thinking of the same looking thing, right? I say the word cylinder, everyone's like, yeah, James, you mean this, right? And usually, yes, that's what I mean when I say cylinder. But when you take kind of a shape in 2 dimensions that's kind of curvy, and you extend it in its third missing dimension, usually we call that thing a whatever shape you have cylinder. Here's what I mean. Let's say I wanted to graph, and if I want to graph that one, I'm not going to graph that one. Fine, I'll graph it. Let's say I wanted to draw the graph z equal to, yeah, it's not really, yeah, fine, okay. Z equal to x squared plus 1 in 3 dimensions. Well, I know what it looks like in 2 dimensions. So what I'm actually going to do to make my life a tiny bit easier is I'm actually going to draw the 2-dimensional part first. I'm going to say, okay, here's my xz plane. I know it's a parabola shifted up 1. So my z-intercept would be 0, 1, or 0, 0, 1, if you will. And then it's just going to do the usual parabola sort of thing. Okay, but now we're going to extend it in the y direction, right? Because there are no y's. So I'm going to draw in the usual. Yeah, the usual. I feel like I'm giving myself too much. Yeah, let's do that. So there's x, y, z. Now, first of all, I'm taking my xz plane, right, and I'm turning it this way. Right, so it's going to look not as parabolic, right? It's going to look more like kind of like, I'm so not good at drawing this. I'm going to draw over here first to give myself a chance. Right, it's essentially going to do like ooh, that. Oh man, the 3D drawing is always challenging for a James. Yeah, that seems reasonable. It's going to kind of look like that. So we're going to get this kind of deal. Sure, I can do that. And then it's going to extend in the y direction and the negative y direction. But let's just do it in the positive y direction, because I think that's going to be enough to see. So we're going to take this and we're going to jam it over that way. And then the thing about making these drawings look good, if you're actually trying to make them look good, is you want the amount to extend it from one point to be the same as the amount to extend it from another point. So like I'm trying to extend it the same amount from this point here. So like over to there. And then the same deal here. This should be about right there. So it should come down like that. And yeah, sure. Okay. And then we connect this up like this. We fill this in because it's not being blocked off. And there is your parabolic cylinder. We call it a cylinder because it's some kind of surface that's been like just, you've taken something and you've extended it in a direction. Lots of things get called cylinders. Even things that don't really, like this doesn't really encompass any volume. Usually I kind of at least think of a cylinder as encompassing a volume, but it doesn't have to. Yeah. So there's a cylinder. It's kind of a weird cylinder, but it's a cylinder. Here's a more normal cylinder. Like, what do I want to do? Yeah, let's do that one. Let's do y squared plus z squared equals to 16. So y squared plus z squared equal to 16 is a circle centered at the origin, radius of 4 in the YZ plane, which is my favorite plane. Sure, there's a circle. And then we're extending it in the x direction. So, right, here's the easiest way to do that, I think. Pick a point down here, try and draw essentially the same, pick a point that's far enough away actually so they don't overlap when you draw them. Ooh, gosh, try and draw the line straight. So pick a point like down here, and then you're just gonna try and draw this same circle. So I'm gonna go up that much, and then down the same amount, and then over the same amount, sure, and then over the same amount. Try and draw a circle. And you're like, okay, and then, right, this part connects to that part. And this part connects to that part. And this part maybe you don't want to draw. Right, so like, not my best picture ever, right? Because really, you kind of want it to look more like this. Or not. You want it to look not like trash. Yeah, my cylinders need some work. Oh gosh. Yeah, I used to be better drawing. Anyway, hopefully you kind of get the idea with the pictures. Again, I should finish it up. It's not so important that you're able to draw them, clearly. What is important is you're able to identify what they look like by the equation. So looking at this equation, we're like, oh yeah, we've totally got a circle, and we're totally missing x, so we know it's going to be a circle extended in the x direction, which is a cylinder. A normal cylinder, not like one of these other weird parabolic cylinders. A couple other things we have to deal with. Sometimes we don't just have an equation, we have an inequality. So if someone said, instead of what I just did, someone said we have like x squared plus z squared less than or equal to 9. Well, I know that x, so what I usually do when I see something like that is I ignore the inequality for a second. I'm just like, okay, well, what if I was doing x squared plus z squared equal to 9? I know that's a circle, radius 3, center at the origin in the xz plane. So I'm going to go 3 up, 3 out, 3 back, 3 down. 1. So drawing a circle in the xz plane, I always find challenging. I mean, you guys can tell me, and I find most of drawing these things challenging. So there's my circle in the xz plane. And then I want to, well, first of all, I want to note that if I want x squared plus z squared to be less than or equal to 9, here's the thing with inequalities and shapes. That circle is my boundary. If we have an inequality, it means we are either on one side of the boundary or on the other side of the boundary. So which side of the boundary am I on? Am I in the circle or am I outside of the circle? Well, maybe I should draw the circle over here so it's a little bit easier to tell. So here's my circle of radius 3. Here's how you tell. Pick any point. Literally any point. Preferably a point that you can already tell is either in the circle or outside of the circle. I'm going to pick the point 0, 0. Does 0, 0 satisfy this inequality? Yes, 0 squared plus 0 squared is definitely less than or equal to 9. So that means that 0, 0 is part of the boundary, the side of the boundary that we want. So we want everything that is inside the circle, because the one point we tested was inside the circle and it was a yes. So what that means is when I draw this cylinder, we don't just want the boundary, we want everything in the cylinder. So the difference between this equation and this equation is that this equation is just the surface. It's kind of like it's like a glass, right? Right? It's just the ends of the glass, it's not the inside stuff. Whereas this equation would be like a solid cylinder, which I don't have a good example of it. I guess it would be like this jar of balm, which is full of stuff, right? That's what we're getting here. We get all the insides. Whereas this here, this is just the shell of the surface and none of the inside. Okay. Let's see, what else have we got here? Oh yeah. Okay, we're doing good. Probably, could we think of the first one like it? Yeah, totally like a tube. Yes, yeah. Because it wouldn't really be, you're right, it wouldn't really be like a glass because you wouldn't have this side here. Well, I've got like a little, I've got what are those things called? They're like the little plastic rolly things to like get the skin off of garlic. You do kind of like this. This thing, right? This is totally like that, pointed out at you. Right, we don't have the insides. Whereas this one's filled in. Okay, yeah, like a tube, totally. So one more, so I should say, there are lots and lots and lots and lots of shapes in three-dimensional space. And oh, actually, before we get going here, I should, let me give you guys one, let me share something with you. Let me show you something. Oh, come on. Sorry, I'm just trying to get to the one thing I want to see. So here is a link. If I can find it, I'm super smart. Yes, 3D graphing. Cool. So here's a link to kind of a little 3D graphing thing that somebody wrote for Desmos. And I think it's useful just to kind of help you visualize things. So let me kind of show you for just 1 second. So here is the link I just sent you. This is the function that somebody started with. I'm gonna delete that. So let's say I want to do the one I just did. Y squared plus z squared equal, oh, so actually I should point out here. So yeah, this maybe is not super useful. I thought it was. So this is not as useful because this is specifically written as z as a function of x and y. So if I wanted to do that one, I would need to write it as z equal to the square root of 16 minus y squared, which you can still do, but it does require a little more doing. I don't need these. So now the thing is I'm only getting 1/2 of it because I'm not getting the plus or minus. But if you slide these things around, you can kind of see how that looks kind of like, I feel like I'm missing a little bit there. It looks like kind of the top half of a cylinder, but right, okay. Maybe not the best I've ever done. But you can also do, yeah. So I'm disappointed by this. I want it to be better. It's not better. Yeah, that's too bad. Such is life. You don't always get it. What about this one? Yeah, okay. No, this is something else as well. Oh, wow. I'll look around and see if I can find a better 3D graphing tool. Not that I think you guys really need it, but it's kind of nice to be like, okay, I don't really know what this thing looks like. Let me throw it into this thing, and then I can kind of get a better idea of what the surface looks like. There is one more surface I did want to mention, though, which is something like this. what if you have x squared plus y squared plus z squared equal to 25? So we know that x squared plus y squared equal to 25 is a circle of radius 5. X squared plus y squared plus z squared equal to 25, that's going to be a sphere with a radius of 5 centered at the origin. So, right, 5 this way, 5 that way, 5 this way, 5 that way, 5 this way, 5 that way. Sorry, so we've got a sphere. With a radius of 5. Now, why is this true? Well, I guess what's really kind of important here is how the distance formula in 3 dimensions works. So in 2 dimensions, right, if you've got a point x1, y1, and a point x2, y2, the distance between them is the square root of x2 minus x1 squared plus y2 minus y1 squared. There is an equivalent in 3 dimensions. In 3 dimensions, it's, so if you've got a point x1, y1, z1, and x2, y2, z2 in 3 dimensions, then the distance is the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. So it's very analogous to the original distance formula. You're just kind of adding on a third thing here. And so basically the idea here is that if you're trying to say, well, this point right here, x, y, z, well, any point on the sphere is a distance of 5 from the center. So the distance between this point and the center, square root of x minus 0 squared plus y minus 0 squared plus z minus 0 squared equals 5. But that equation and that equation are exactly the same. You just square both sides. Or you square both sides of this equal to this. So when you see something like x squared plus y squared plus z squared equal to a number, that's going to be a sphere. And we can even go a little bit more general. If I said, okay, what about this equation? X minus 2 squared plus y plus 1 squared plus z squared equal to 9. This is a sphere. I feel like I'm not great at saying the word sphere. Sphere. Yeah, okay, yeah, it's not my best. Sphere. I feel like I'm saying, I feel like I'm going to roll to the S there. Anyway, this is the equation of a sphere with center. Just like with a circle, it's the things that make each part 0. So the center is 2, -1, 0, and the radius is 3. We could try to draw it. I don't really want to. If we tried to draw it, our center would be 2 in the x direction, and then 1 in the y direction. Sorry, -1 in the y direction, and then 0 in the z direction. And then from this center point, we have to go 3 in each of the 6 directions. So 1, 2, 3 to the right, and then 1, 2, 3 to the left, and then 3 up, and then 3 down. And I'll probably start with that. Like there's my, whoops, wow. So clearly not the best, right? And then we would say, we're going to go 3 in this direction as well. So yeah. So there would be your sphere of radius 3 centered at the point 2, -1, 0.